Welcome and thank you for joining. In this lesson, we're exploring function continuity, and in this case, we're going to take a look at this very interesting example. So we have kx equals absolute value of x minus 3 divided by x minus 3. As you can see, we have a rational function that contains an absolute value. Now, before we go over this example and discuss its continuity, I want to talk a little bit about the absolute value functions, or let's say absolute value numbers. That's where we start from. Remember that the absolute value of a number indicates the distance of a number from the origin, which means that, for example, if this is the number line and we have, say, for example, number 5 somewhere on the right side of it, we'll say that the distance of number 5 from 0 is 5. So instead of writing the distance, we write absolute value. And since distance is always measured by positive numbers, then we'll say the absolute value of 5 is 5. Similarly, we're going to say that if we have negative 5, which is a number on the left side of 0, the distance of number negative 5 from 0 would be equal to 5. That's because distance is measured with positive numbers. So we'll say that the absolute value of negative 5 is a positive 5. So generally speaking, we say that the absolute value of any positive number, say absolute value of 3 is 3, absolute value of 124 is 124, and absolute value of any positive number would be equal to that positive number. And if the number were to be unknown, but we knew that absolute value of x, of some unknown positive number, would always be equal to x, providing that x is either a positive or equal to 0 number. However, when we talk about the absolute values of negative numbers, for example, absolute value of negative 3, then the answer would be positive 3. Absolute value of negative 7, that would be equal to positive 7. So as you can see, the absolute value of a negative doesn't equal itself, but absolute value of a negative would be the opposite, we say, of itself. So the number 3 can be also described as negative, or the opposite of negative 3. So absolute value of negative 7 is 7, or we're going to say that it is the opposite of the number that is inside the absolute value. So therefore, in general, we're going to say that if we have a negative number inside the absolute value, then the answer would be the opposite of that negative number. In general, if that number were to be unknown, so if we have the absolute value of x, providing that x was a negative number, then we'd say that the absolute value of x would be equal to the opposite of x, because remember that this would be negative. So negative and negative will make a positive answer. So generally speaking, then we are going to say that the absolute value of x, and I'm going to have to erase this and I'll put this definition in here. So we'll say that the absolute value of x would be equal to x if x is positive or 0, and the opposite of x if x were to be a negative number. Now, in our case, what we have is the absolute value of x minus 3. So when we discuss the sign, or the absolute value of x minus 3, then we're going to say that the absolute value of x minus 3 would equal itself. So it would be equal to x minus 3 when? If x minus 3 were to be positive or 0. So the value of this expression is positive or 0. Now, when does that happen? It happens when x is bigger than or equal to 3. So where do we get this from? Just take negative 3 to the other side. This is a simple basic inequality. So we're going to say that x minus 3 in absolute value would equal itself if x is bigger than or equal to 3, and it will equal the opposite of itself if x minus 3 were to be a negative number, or we say if x is less than positive 3. Now, you're probably wondering, why do I have to know all this? Well, the thing is, when we discuss the continuity of a function, we need to find the limit of a function at a point. And when we determine the limit of a function at a point, we need to remove the absolute value. And removing the absolute value has to be done carefully, because we cannot just remove it in any way we want. We cannot just use an eraser to remove it. That would be funny though. But we have to respect the terms that are inside, and we have to respect how the absolute value works. Okay, so now let's start with discussing the continuity of this function. So the first thing that we want to do is check and see where this function may be discontinuous. Since we are dealing with a rational function, then the potential discontinuities would be wherever the restrictions are. So as you can see in here, we have x minus 3 in the denominator. So x minus 3 different than 0 suggests that x has to be different than 3, which means that the function is undefined at x equals 3. So that will make a potential discontinuity point. So when discussing the continuity, we'll focus on x equals 3. So we're going to say that if we were to evaluate the function at 3, so k at 3, it means that we have to substitute x by 3. We get 3 minus 3 over 3 minus 3, which will be 0 over 0. So this is undefined. So we understand that the function is undefined, which means that there will be some type of discontinuity here, but we don't know exactly what type of discontinuity it is unless we have explored the limit of the function. Or in other words, we will have to now find the limit as x approaches positive 3 from the left-hand side, and the limit as x approaches positive 3 from the right-hand side. So if we want to find the limit as x approaches 3 from the left-hand side, then we have to check and see what happens to the equation of this function, which is absolute value of x minus 3 over x minus 3. Now, we cannot determine the limit when the function still has the absolute values on. So first we need to remove the absolute values. When x approaches 3 from the left-hand side, it means that x approaching 3 from the left-hand side, it means that we need to take the opposite of x minus 3 when removing the absolute value. So therefore, we're going to say that that would be equal to, I'm going to write it down actually here. So that would be equal to the limit as x approaches 3 from the left. So to remove the absolute value, we are taking the opposite of x minus 3, because we know that x minus 3 will be a negative number for all the x values to the left side of 3. And that would be over x minus 3. So as you can see here, we have x minus 3 and x minus 3 common. So that will make this the limit as x approaches negative 3 from the left, of negative 1. So this limit is what we call the limit of a constant, so that would be equal to negative 1. So the left-hand limit is equal to negative 1. Now let's take a look at the right-hand limit. So for the right-hand limit, again, we're going to write the equation of the function. So the equation of the function absolute value of x minus 3 divided by x minus 3. Now, when x approaches 3 from the right-hand side, remember we need to remove the absolute value, otherwise we cannot estimate the limit. So when x approaches 3 from the right-hand side, then we are going to say that the piece of the function that we're using here would be x minus 3. So it means that when approaching 3 from the right-hand side, this will be a positive number. So when removing the absolute value, we are going to keep x minus 3 as is, because the absolute value of a positive number equals the number itself. So, and down here we'll have divided by x minus 3. So as you can see, x minus 3 and x minus 3 will simplify, and that would give the limit as x approaches 3 plus of number 1. And that would equal exactly 1, because that's the limit of a constant. So as you can see in here, when x approached 3 from the left, the limit was -1. 3 from the right was +1. So positive 1 and -1 are two different numbers. So we're going to say that the left and right hand side limits are different. So I want us to think, what kind of discontinuity do we see when the limit of a function is different on the left and right side of it? So the limit is different and is approaching a specific number, which means that we are going to see a jump discontinuity, because there is not an infinite gap between the y values of the function at x equals 3. So that means that this is a jump discontinuity example. Now, if you were to draw the graph of this function, so which we will right here, I think we have enough space, kind of. So we're going to say that the value of the function at x equals 3, so there goes number 3, doesn't exist, so the function is undefined. But when we approach 3 from the left-hand side, the value of the function becomes -1 and is constant, no matter what x becomes, or whatever, no matter what the value of x is. So therefore, we're going to say that, I'm just going to bring number 3 a little bit higher. So here is -1. So we're going to say that the value of y would be equal to, or will approach -1. So it will be -1, and at x equals 3, it will be undefined. Now for x values greater than 3, here is number 3, we are going to see that the value of the function becomes 1. And obviously is undefined at x equals 1. And that would be this would be the graph of the function kx equals x minus 3 in absolute value over x minus 3. As you can see here, we have a jump discontinuity, or a measurable gap between the two pieces of the function. Now, the last example in this lesson is illustrated by this graph. So as you can see, we have all kinds of discontinuities. We have so many pieces in here. So we'll discuss the continuity of a function at some specific points. We're starting off with x equals -3. So at x equals -3, you see that the value of the function is defined. So we'll say that f at -3 equals +1. The way you find it is just go up until you hit the graph of the function and see if it has a specific value. It's a fill dot, so the value is 1. Now, next we are discussing the limit as x approaches number -3 from the left-hand side, and the limit as x approaches -3 from the right-hand side. So as you can see in here, when you approach the left side of -3, the values of y are going towards 1. When we approach the right side of -3, the values of y are still becoming 1. So the limit on the left and right side is the same, and that means that the limit at 3 exists. -3 of f of x exists, and it equals 1. If you compare the value of the function at -3 and the limit of the function at -3, then we can tell that these two are equal, which means that the function is continuous at x equals -3. Now, in a similar way, we'll analyze the continuity of the function at x equals, this time, -2. So we'll start off by finding the value of the function at -2. So again, the way we do it is go at x equals -2, move vertically until you hit the graph, and you see that you hit a hole in here, which means that the function is undefined at negative 2, which means that we must have some type of discontinuity. But to understand the type of discontinuity, we need to take the limit. So take the limit to the left. You see that when you approach on the left side of negative 2, we see that the y values are getting closer to positive 2. When we approach the function from the right side of negative 2, the values of y are becoming positive 2. So that means that the limit as x approaches negative 2 from the left-hand side equals the limit as x approaches negative 2 from the right-hand side, and it is equal to 2. Therefore, we are going to say, since the limit exists, it's just a function that is undefined, which has created a hole, and the hole is created from a removable asymptote or removable restriction, then we're going to say this is removable discontinuity. At x equals negative 1, so let's move on at x equals negative 1 now. Let's get this out of the way. So what you see in here is that at x equals negative 1, the value of the function is defined. So we're going to say that f of negative 1 is equal to positive 1. Now, when we look at the limit of the function when we approach negative 1 from the left and right-hand side, so here is negative 1, I'm approaching negative 1 from the left-hand side, you see that I have to hit the graph in here, so this piece of the graph. So those are the y values. So the limit on the left side will be positive 2. So limit when x approaches negative 1 on the left side of it will be negative 2. Limit when x approaches negative 1 on the right side of it. Let's take a look at the right side. So here's negative 1. Here's the right side of negative 1. So the graph we hit in here is this piece, which suggests that the values of y are approaching positive 1. As you can see, the left and right hand limits do not agree. The function is defined though, but the fact that the limit is different suggests that there is a gap on the graph of the function, and this is a measurable gap because these two are fixed numbers. So that will make this a jump discontinuity. Okay, and in the next example, we're looking at x equals 1. So at x equals 1, we have the function defined, and it has a value of 1. So f of 1 equals 1. Now let's take a look at the limit. So as you can see here, we have approaching 1 from the left. The value of the limit will be positive 2. So you see that as we approach 1 from the left, we have to hit this part of the graph. And when we approach 1 from the right, we are hitting this part of the graph, okay? So, which means that the limit on the left is 2 and the limit on the right is 3. So we're going to say that the limit as x approaches 1 from the left-hand side of f of x is different than the limit as x approaches 1 from the right-hand side of f of x. So the fact that the limit is different and they are actually approaching a fixed number, so one side is 2 and the other side is 3, suggests that there is a jump discontinuity. But because the function is also defined at 1, so we have this point here, then we're going to say that it's a combination of jump and a point discontinuity. So we're going to say that point discontinuity can be associated with jump or it can be associated with removable. So it's not a type of continuity that goes on by itself. And that's why when we discuss continuity, we just threw it with a group of removable discontinuity in there so that we could understand it better. So at x equals 3, so let's see what happens there. So at x equals 3, we have the value of y equal to 1. So we'll say f of 3 is 1. So the function is defined so far. Now let's take a look at the limit. So when we are approaching here the limit as x goes towards 3 from the left-hand side, you see that on the left-hand side, the values of y are going close to 1. Now, let's take a look at the limit as x approaches 3 from the right-hand side this time. So here is number 3. Here's the right side of it. So I'm getting closer and closer to it. And you see that the values of the function are approaching infinity. So as you can see in here, we have two limits that are in disagreement with each other. So there is definitely a break in between. But because one of the sides of the limit is going to infinity, that makes the break infinite in size. And that's what makes this type of discontinuity an infinite discontinuity. Okay, so this is the last example for the lesson on continuities of functions, and I hope this all made sense. And I hope you enjoyed learning and understanding how functions work and how different types of continuities are sort of connected to each other. I hope you find it useful, and thank you for watching again. Bye for now.